Hi, everybody. Thank you so much for tuning in today. I'm excited to introduce our seminar speaker this week, Dr. Parvarti Prem, who is currently a staff scientist at Johns Hopkins Applied Physics Laboratory in Maryland. Dr. Prem is a planetary scientist whose research has most recently focused on modeling the origin and transport of volatiles, mainly water, on the Moon and Mercury. Although I would say she's generally interested in using computer models to characterize the interactions of planetary bodies with rarefied atmospheres with space. She grew up in England and in India, but pursued her undergrad studies in Singapore at Nanyang Technological University, where she received a bachelor's degree in aerospace engineering. She then pursued a master's and PhD at the University of Texas at Austin, both in aerospace engineering, where she worked in the computational fluid physics lab, where she got into planetary science. And so she got into that during her grad studies. After her PhD, Dr. Prem did her postdoc at Johns Hopkins, where she then transitioned to her current position about a year ago as a staff scientist, as I mentioned. She's a science team member of NASA's Lunar Reconnaissance Orbiter, so LRO, that mission, and also part of the SEAL payload. And she's also a co-investigator in two survey teams. And actually, recently, she just received an award, an early career award from Survey, which I was really excited to see and wanted to formally congratulate you for that award. And so I'm really excited to have Dr. Prem talk to us today. And I guess with that, welcome and take it away. Thank you again.
All right, awesome. Let me get my screen share going. And thanks so much, Francis, for the lovely introduction and for the invitation. And thanks to all of you for taking some time out of your day to listen to me today. And if you stick around, I can show you the award. It's like in a box next to my desk because I have to take it to the office. But anyway, so yeah, I was really excited to get the opportunity to talk to all of you. I think you have a really great interdisciplinary group there. So I'm glad we get to meet and talk today. So I'm assuming everyone can hear me and see my slides okay. If things sound weird or you're not seeing what you should be seeing at some point, just give me a shout. But yeah, so my presentation today is titled "The Once and Future Lunar Atmosphere: Modeling the Moon's Water Cycle." So you might wonder what a lunar scientist is doing in an astrobiology seminar. And I think part of the answer is that thinking about water on the moon is also a way to think about some other interconnected big questions. The story of water on the moon is also a story of how the ingredients of life, including the water molecule, reach the inner solar system and the Earth-Moon system in particular. It's a story of atmospheres, what it takes to sustain an atmosphere, how atmospheres change over time. And it's also a story that touches upon aspects of planetary protection and on how we interact with extreme environments and with other worlds beyond our own planet. The image in the background there, it looks like the animation might not be playing, but that's okay. I can share the slide later, and it looks good even without the animation, I think. So, if I say so myself. But I'm a modeler, and I think one of the ingredients that goes into modeling, besides the physics and the math and the computer programming, is a little bit of imagination. And so I put this image together. It's our moon superimposed over a sequence of New Horizons images, even though it might seem to be stuck on one image. But this shows, this was sort of my way of imagining what the moon might have looked like at some point in the distant past. So this would be long before life started to take root on Earth. But if you'd been around back then on the primordial Earth and looked up in the sky, you might have seen a sight, something like this. So as Francis mentioned, I work at APL. I'm in the Planetary Exploration Group, which is has the bizarre acronym of SRE, which stands for Space Research Exploration. But we're the Planetary Exploration Group. It consists of around somewhere between 40 to 60 planetary scientists. Everyone majored in different things and got there in different ways. But we are the planetary science group at APL, and we have these 7 different sections within SRE that focus on a whole range of things, from small bodies to exoplanets. I'm actually in SRE3, the spectroscopy group, but there's very little spectroscopy in this talk, and planetary science being the wonderful syncretic field that it is, all of us do work that touches on more than one of these themes. It's a great place to work, and all of you are very welcome to visit if you're ever in the neighborhood. Come on down. We'll have lunch at the food trucks, and we'd love to meet you and learn about your research and get to know you better. We like visitors, so shoot me an email if you're ever in the neighborhood. So getting to our story of water on the moon, I sometimes think of water as the molecule that launched 1,000 spacecraft, because when we think about some of the big questions in planetary science, whether it's how the ingredients of life reached our home world, where else in the solar system those ingredients are present, and why they are distributed the way they are, the water molecule is central to some of those big questions. We live on a planet where we're surrounded by water. It's in the atmosphere, in the oceans, in the ice caps. And so you might wonder, why go to the moon? And the answer, as the answer to some other questions also is that the moon preserves a record of the ancient history of our solar system neighborhood in a way that perhaps no other solar system world does. And the geological record that the moon preserves is present not only in its craters and in the silicates and the refractory rock-forming elements. There's also a geological record that's written in volatiles, including H2O. And it's hard to talk about water without recognizing the fact that because it's so integral to life as we know it, there's a lot of interest in using lunar water as a viable resource in some way. So we're still very much in the process of understanding whether water on the moon could be a viable resource, and we're only just beginning to deal with the question of, if it is, how do we use that resource responsibly? But that's another question that motivates some of this work. And I do briefly want to mention that although I'm going to focus mostly on water, on H2O today, it's only one of the many volatile molecules that make up the lunar volatile system. One of the most abundant lunar volatiles is argon, helium, other noble gases. Argon can be outgassed from the lunar interior. Helium comes mostly from the solar wind. Those are some of the most prominent lunar volatiles. In fact, they tell us a geological story about the moon today. There are also alkali metals that are volatile. So, for instance, one of the only volatiles you can see from Earth is sodium. If you look at the moon through a telescope at the right wavelengths, it's all aglow. It has this halo of glowing sodium all around it. That's kicked up by micrometeoroid impacts and by charged particle sputtering. But our story today centers on one of those volatiles, the water molecule. And so we have our molecule, our leading player. And we also have a strange environment that records the history of that molecule over time. And these are the permanently shadowed regions near the lunar poles. So what are PSARs? When the moon has a peculiar orbit in some ways. As the moon orbits the sun, it rotates along an axis that's almost perpendicular to its orbital plane. And what that means in practical terms is that near the lunar North Pole and South Pole, the South Pole is the one that's pictured in these images on this slide. But near the lunar poles, the sun is always extremely low on the horizon. It never rises more than about 5 degrees in the sky. And what that means is that if you have any craters or any kind of topography, it ends up casting long shadows that are extremely dark and persistent. And you can see some of those shadows in this visible light image from the camera on board the Lunar Reconnaissance Orbiter spacecraft. These shadows are not only dark, they're also extremely cold, as you can see in this map of average temperature here. The temperatures go down to 50 kelvins and less. These really are some of the coldest places in the solar system. And they're also extremely old. Some of these crater interiors have been shadowed for more than 2 billion years. So they haven't seen sunlight for 2 billion years, or in some cases even longer. And what that means is that these permanently shadowed regions, which we often refer to as PSRs, are old enough, dark enough, and cold enough to preserve volatile ices over geological timescales and record that history in the same way, or in similar ways, to similar but different ways, to sedimentary layers on Earth. And to put these temperatures into perspective, the temperature scale here also points out the temperatures at which different volatile compounds become stable. Now, just because something is stable doesn't mean it's necessarily present, but just to put it into perspective, sulfur ice becomes stable in the yellows here. As we get down into the blues and the purples, water, ammonia, carbon dioxide, some organics all become stable. And then there's a star here marking a location that was sampled by the LCROSS mission, which we'll talk about a bit on the next slide. This idea that the poles are shadowed and cold and old enough has been around since the 1960s, before humans ever set foot on the moon. And as long as that realization has existed, the realization that water and other ices may be present in those cold, dark shadows has also been around. But we didn't really start getting observational confirmation of some of those ideas until the late 1990s. So the results shown here range from lunar prospective results in the late 1990s all the way through 2009 and just a few years ago. And so what do we know about the presence of volatiles, and specifically water at the lunar poles? Neutron spectroscopy, some results of which you can see here. Neutrons are sensitive to hydrogen in the upper meter or so of the lunar subsurface. And so regions that are blue and dark blue here near the South Pole, the neutron measurements indicate that the subsurface in some regions is hydrogen rich. So we know that there is H present in the subsurface in the upper meter or so. Whether that's H2O, the neutrons alone can't tell us. But we have other ways, other eyes through which to see the moon. Even though permanently shadowed craters are permanently shadowed, and almost by definition there's very little light, there's just enough reflected and scattered light that you can do reflectance spectroscopy. And so the central image here shows results from spectral data analyzed by my colleague Shuai Li and others. And the little greenish dots that you can see there are individual pixels where there are spectral signatures of H2O ice. And so one thing to keep in mind is that the size of the actual pixels are much smaller than the size of these little dots. But it does seem from the spectral data, through if you analyze it carefully enough, that there are these scattered patches of exposed water ice within some of these PSRs. And we also have only one direct detection. In 2009, the LCROSS spacecraft visited one of the coldest regions on the moon, the interior of this old degraded crater called Cabez. What LCROSS did was to spend some time in the vicinity of the moon emptying out its fuel tank, and then it dropped that empty fuel tank, that metal cylinder, into the shadows. And that crash threw up a cloud of debris, of dust and gas, that spectrometers and other instruments on the main spacecraft were able to analyze. And so in visible light, this looks like a smudge, but if you look at it in the near infrared and in the UV, the LCROSS team detected conclusive evidence that water and other volatiles, including some organics, some carbon compounds, ammonia, other things were present in at least that one location. And so we have all of these clues that water exists and other volatiles also exist, but there is still a lot of mysteries around the origin, abundance, distribution, and physical form of water. We don't completely understand what it is that we're looking at. And so we have these observations, and then the challenge becomes reconstructing the past. So before we go deep into that, I think it's sometimes useful to take a step back and consider that the story of water on the moon is also the story of water on Earth, because after all, we live in the Earth-Moon system. You know, the planets tug on each other, we feel the tides, we see the moon in the night sky. We live in the Earth-Moon system. And the story of water goes back all the way to almost the beginning, around 4.5 billion years ago when the moon formed. Our current best guess for how the moon formed is that a large object collided with the proto-Earth, throwing out a cloud of debris that coalesced to become the moon. Now, we think water was present at the time of the moon-forming impact, and one of the major outstanding questions that a lot of folks who do, in particular, sample analysis are trying to figure out is how much of that earliest water went into the moon, how much of it was retained on Earth, where did that water go? For the most part, we think that water is trapped, some of that water is trapped within the lunar interior and can be observed in rocks on some parts of the lunar surface today. After the moon formed, for the next many, many billions of years today, and in fact this is a process that hasn't really stopped, but the moon and the Earth, which of course was much closer, that's why you see it getting smaller in the sky in this sequence of images, the moon and the Earth were bombarded by comets and asteroids from the mid and the outer solar system, and some of those comets and asteroids brought water to the lunar surface and also to the Earth, where oceans started forming and life started spreading its roots and swimming through the oceans. From around 3.8 billion years ago to 1 billion years ago, the moon underwent a period of dramatic and widespread global volcanism. And those eruptions also played a role in the story of water, because when volcanic gases rose from the interior and erupted onto the surface, those lavas carried volatiles that were trapped in the interior to the surface and released them. And in fact, what happened to those volcanic gases is still a little bit of a mystery, but there was also some water there. And even today, when the moon looks fairly quiet, it's still a very active world with what we think is an active water cycle. Water today is delivered by continuous contemporary sources, specifically the solar wind and micrometeoroids. I saw Brant Jones online. This is something he knows a great deal about, but the solar wind, hydrogen from the sun can, under the right conditions, interact with oxygen in lunar rocks to form H2O. Micrometeoroids, which continuously bombard the moon from all directions, can provide enough energy to liberate some of that water. Some of it goes into the exosphere, some of it might make its way all the way to the poles. We're still finding out. And so that brings us to another part of the puzzle. So today we have observations of water trapped in rocks, trapped near the poles, and we have a sense of what the sources were. But between the time that a source delivers water into the lunar environment and the time that that water is trapped in the form, in the geological formations in which we can detect it today, it travels through the lunar atmosphere. The lunar atmosphere today is very, very thin. In fact, it's not really an atmosphere at all. It's what we refer to as a surface-bounded exosphere, in which molecules hardly ever interact with each other. And in fact, surface-bounded exospheres are perhaps the most common kind of atmosphere in the solar system. And just because they're thin atmospheres, just because they're barely there atmospheres, it doesn't mean that they're not interesting. And that's how someone who majored in aerothermodynamics and fluid mechanics ends up studying the moon, because to my mind, I think some of the most interesting atmospheres are the ones on the rarefied end of the spectrum. And so to give you a sort of picture of what that looks like, we can characterize atmospheres in terms of the mean free path, which is the average distance that two molecules collide, or that two molecules travel before they collide in the atmosphere. So on Earth and on some of the larger moons like Titan, molecules only go 100 nanometers before they meet another molecule. As we move away to other solar system worlds, that distance increases. It doesn't increase as a function of solar distance. It's a little less intuitive than that. But Mars, of course, has a much thinner atmosphere than Earth, but molecules still only travel tens of microns before colliding. Then we have increasingly rarefied atmospheres on Triton, Io, Callisto, and then, of course, the Moon. But I think one of the most interesting things about the Moon is that during the course of its history, it's traveled along this spectrum. There may have been times in the past when the Moon had an atmosphere that looked more like Io. Perhaps at some point it looked more like one of these other worlds. The lunar atmosphere has traveled almost across the solar system without even moving over the course of time. That's one of the things I think makes it so fascinating. And so the question that's at the core of a lot of my research is how the lunar atmosphere has changed over time and how that history is preserved. And my method of addressing that question, there are lots of other ways to address it, but my sort of flavor of research involves numerical models. So how do we do this? How do we get a hold of this using numerical models? If you want to model lunar volatile transport, you have to begin with a source. We talked about several different sources. How do you sort of grasp those and put them into a numerical model? And again, this is my way of doing this. And so I wanted to spend a couple of slides on method to give you an idea of how we arrive at some of the results that I'll show in the next few slides. And so let's consider two very different sources of volatiles, one that's natural, a comet impact, and one that's anthropogenic. Spacecraft, as it turns out, also release water vapor when they fire their engines to land on the lunar surface. But ultimately, my way of modeling this is to consider the fact that all of gas dynamics is really ultimately about the motion of molecules. And in this case, we're focusing mostly on water molecules. We know that if you have a comet that strikes the surface, you get a cloud of vaporized gas and dust, and ultimately that vapor, part of it at least, is just water molecules. Similarly, in the case of spacecraft, we have a reasonably good theoretical idea of what happens when hot rocket exhaust gases expand into vacuum, and we can use that information and convert it into molecules. If we know the density, temperature, and velocity of a source mechanism that generates water vapor, we can package that information into molecules and then understand the gas dynamics by understanding what happens to the molecules. So we have our source. But where things start to get really interesting is when those molecules interact with the lunar environment. And so here we have the environment. And you'll see a lot of processes here. And I think the main takeaway message is that even rarefied atmospheres, even surface-bounded exospheres, where there's hardly any atmosphere at all, those exospheres are really rich in physics and chemistry. Almost every one of these processes that you have here is a subject of active ongoing research. And so what happens to those molecules that come from a comet or come from a spacecraft or the solar wind or micrometeoroids or anything else? For the most part, when the atmosphere is thin enough, those molecules travel under gravity. They travel along these ballistic, hopping, bouncing trajectories. Or, at least that's what we think, based on the knowledge that we have today. Sometimes those molecules can collide with each other. When they do that, they exchange energy and momentum. We can model that using a technique called the direct simulation Monte Carlo method, which I won't go into in detail unless anyone's interested and has a question. But it's a way to model that exchange of energy and momentum. Molecules can also undergo chemical reactions. Some of the simulation results that I'll show you today don't include chemical reactions, but it's important to keep in mind that that is a process that can take place. When molecules interact with the surface, they can stick to the surface, they can absorb for some period of time that depends on the local surface temperature. If the surface is warm, molecules tend to hop away. If the surface is cold, they tend to stick around for longer. Molecules can also land in cold traps in permanently shadowed regions where they can be retained for geological timescales. And molecules can also escape the lunar volatile system in several ways. So the sun is really the great destroyer of water and many other molecules. Solar ultraviolet radiation can break apart H2O into lighter molecules that escape more easily. Sometimes when a molecule lands on the surface, it can leave the surface so fast that it zooms out of lunar gravity. It can undergo thermal escape. And then there's also radiation of different flavors and kinds that can affect the energy that molecules have. So not all of these processes are important all of the time, but this does give you a picture of all of the physics and chemistry that make up this environment. And so what does it look like when we put all of that together? I wanted to spend a couple of slides talking about one particular case study. This was work that I did during my PhD, looking at what happens to water that's delivered by a comet impact. The reason for focusing on that particular source is that some of the measurements that we have, particularly from the L-CROSS mission that dropped a metal cylinder into a permanently shadowed crater, some of the measurements from L-CROSS suggest that perhaps those volatiles that L-CROSS sensed may have come from comet impacts. And of course, we know that this is a process that has happened through time because we see so many craters all across the lunar surface. And so this animation that's running here shows you what you get when you have a comet around 2 kilometers across hitting the North Pole of the Moon. So the comet came in at t=0, it hit the North Pole, and it became a cloud of water vapor that you can see expanding around the Moon here. And the colors indicate velocity. So it's initially traveling out at tremendous speeds. Over time, you get slower moving vapor moving out from the point of impact, and some of it starts to fall back to the lunar surface. And the TLDR version of some of my dissertation work is that what happens to that water depends strongly on impact parameters. So it depends on things like the size of the comet, the speed, the angle at which it comes in, even the location. And I only really began to just scratch the surface of that in some of my work. But again, some fraction, irrespective of impact parameters, some amount of those volatiles, of that water vapor from the comet, can remain gravitationally bound to the Moon, forming a temporary atmosphere. And that temporary atmosphere turns out to be a particularly interesting one. This is a different view of that atmosphere. The colors now indicate gas density in units of molecules per cubic meter. And just to put this in perspective, the density of the Earth's atmosphere in those units is 10 to the 25 molecules per cubic meter. So this is a very thin atmosphere, but you can see that it has a structure that's not quite like any other kind of atmosphere. And this is a time sequence. The animation shows the evolution of that atmosphere from around 1 hour to 6 hours after impact, and then here's it and still. In fact, this atmosphere, this evolving, changing, gradually disappearing atmosphere can last for a few lunar days before sunlight breaks it all apart. And it has this interesting characteristic structure. And that structure is important because it determines what ends up staying behind near the poles. So for instance, in this case, we had an impact at the North Pole. We have this vapor expanding outward. It falls back to the lunar surface, and it cools down so much as it expands away and falls back at such a high speed that you get a shock. Which is what you can see here in the oranges. So what happens is you have this cold, low-density vapor falling back. It undergoes a shock. It gets compressed. It gets heated. It gets transformed into winds that sweep across the surface from in this case, from north to south and from day to night. And it's those winds, it's that atmosphere that ultimately delivers some water to cold traps where we can see it today. And this is really just one part of the history of the lunar atmospheres, of the lunar atmosphere. Impact-generated atmospheres, we think, are only one kind of ancient lunar atmosphere. And based on a great deal of research by so many colleagues that I didn't have the space to put in all the references, but we can talk about this in much more detail if folks have more questions about this. But here's sort of a big picture view of what we think we know. And and what I personally like about this slide is that there are hundreds of research questions in here, and there are so many different ways of answering those questions. And so I would love for people to take these ideas and really run with them. But here's some of what we know and some of what we don't know. We think the first kind of lunar atmosphere to exist was a primordial one. Near the beginnings of the Earth-Moon system, the Earth and the Moon were so hot that they outgassed heavy volatiles like sodium and even silicon oxide, hot, vaporized, rocky stuff. And this is not purely theoretical. In fact, some exoplanet observations indicate that there might be exoplanets, rocky exoplanets close into their stars that have this kind of an atmosphere that resembles what we might have seen on the primordial moon. That atmosphere lasted until the surface cooled, until all of that magma became rock. And we think it was a fairly dense one, falling in the continuum regime of atmospheric density. Some of my colleagues, Prabal Saxena, NASA Goddard, and others have tried to think through how we could possibly know whether this really was the case, what traces would be left behind today. And some of the ideas that they've come up with is that maybe if you look at the samples in particular, you might see telltale differences in surface composition between the side that faces the Earth and the far side. And that might be a way to understand what the moon looked like all the way in the first few tens to hundreds of millions of years after it formed. Then we have volcanically generated atmospheres, which in some sense remain the most mysterious. We know that volcanic gases probably mostly consisted of carbon monoxide, with trace amounts of some of these other compounds, including H2O. We think that these atmospheres may have lasted from anywhere from hundreds to millions of years. And the evidence today, some of it might be preserved at the poles. Some of those volcanic gases may have made it all the way to the poles. But we know that there are also traces in pyroclastic deposits. So some volcanic material, as it erupts outward, cools so fast that it traps some of those volatiles in these really quite beautiful glass beads that you can see in some lunar samples. Those tell a story about what was outgassed all of those years ago. And then you have impact-generated atmospheres, which are more cometary or asteroidal in composition. They were probably the most transient. They may have lasted only for a few lunar days. They were mostly very thin, though also very dynamic. And the traces, again, might be preserved at the poles, and also, in some cases, in impact glasses. So some of the water generated by an impact can be trapped in glasses in the vicinity of impact craters. And so we start to have this picture. And if we, again, take a step back and consider some of the big picture questions. Where we are today after, a few decades of modeling and observations and thinking through things, we know that the lunar surface, especially near the poles, has a unique record of the history of water in the inner solar system. We also understand a lot more about PSRs than we did. We know that they're some of the coldest places in the entire solar system. Some lunar PSRs are colder than the surface of Pluto. And when you have those extremely cold microenvironments where the energy sources are almost astrophysical, the only energy sources are charged particles and far UV radiation, There's almost we've really barely begun to scratch the surface of the processes of the chemistry and physics that happens in those conditions. And because of these realizations and some of the questions that we don't have answers to, there's a lot of interest in returning to the lunar surface, which which is a location at which you can understand the volatile system in ways that you can't always through remote observations. There are some measurements that are best made at the lunar surface. But when we think about returning to the lunar surface to study H2O, we run into a peculiar and interesting problem, which is that almost any landed mission is going to be an active volatile release experiment. If you're sending a lander to the lunar surface to study H2O, you're bringing H2O with you, and it's very hard to avoid that, simply because the moon has such a thin atmosphere that it's not going to slow a spacecraft down all by itself, so a spacecraft needs to fire its engines. When you burn rocket fuel, you end up releasing exhaust gases into the environment, and some of those exhaust gases include H2O. And so there's an opportunity and a conundrum that you need to tackle when you're landing at the surface. There's an opportunity because you're almost inevitably going to conduct this experiment. If you observe where all of those gases, including the H2O, go, what happens to those gases, that teaches you a lot about how water interacts with the lunar environment. But there's also an operational need to understand that same problem. If you're going to a location to figure out how much water is there, how it's distributed, what its isotopic composition is, you need to understand what happened to the water that went with you. And this sort of general problem of separating anthropogenic sources from what's already there is something that has implications beyond the moon. So for instance, there's been some work recently considering how some of the nitrogen compounds released by a spacecraft might affect measurements of trace biosignatures and other nitrogen-bearing species if, for instance, you were to land on Europa. And so to begin answering that question, some colleagues and I recently modeled what would happen to the water vapor released by a spacecraft. And this is a snapshot from one of our simulations. So in this case, you have a spacecraft. It's descending along this trajectory that you see here. At 25 seconds after it started firing its engines, it's right about here. And so you can see this dense jet of water vapor coming out of the spacecraft. The spacecraft itself is way too small to see on this scale. I mean, note that the spatial scale here is in kilometers. So the spacecraft is tiny in the scheme of things, but there's this tremendous jet of water vapor that spreads out from the spacecraft and interacts with the surface, which is at the bottom of the graph here. The density here is in slightly different units of molecules per centimeter cubed. And to put this in perspective, the density of the lunar exosphere under usual conditions is 10 to the 4 molecules per centimeter cubed. So you're seeing many, many, many orders of magnitude increase in the density of the exosphere when you have a spacecraft introduced into the system. And that water vapor continues its journey. In fact, it's globally dispersed. So if we zoom way, way out, our simulated landing was at 70 degrees south around here, 20 degrees in latitude from the South Pole. And this is a time series showing how water vapor spreads through the exosphere at 3 hours, 6 hours, and 24 hours after landing. You can see that the water vapor not only travels through the exosphere, it's also deposited on the surface. The purple sphere that you see here is the purple hemisphere is the lunar night side, which is so cold that any water that falls back onto the night side tends to stay there until the surface warms. One of the other interesting things that you can see here is that there are two scenarios, there are two possibilities for what might happen, depending on how strongly water sticks or absorbs to the lunar surface. And that's where one of the interesting scientific aspects of this comes in. If we could observe the lunar surface and exosphere during a landing and predict what we might expect to see depending on how strongly water absorbs to the lunar surface, we can compare model predictions to observations to try and figure out what really is going on. How does water interact with the lunar surface? And that has implications not just for predicting things like contamination, but also for understanding how even water delivered by comets or other sources might have interacted with the lunar surface many, many years ago. And another parameter here is, of course, the size of the lander and how close it lands to the poles. That also affects the answer that you get. And I think one of the scientific investigations that I'm most looking forward to in the next few years, whether I'll do it or someone else does it, I'm not sure. But irrespective, there are several upcoming missions that offer the opportunity to see what really happens and to understand better how water and other volatiles interact with the surface of our solar system bodies. So, for instance, NASA has a rover called Viper. Its landing site is going to be announced on Mondays. There's a press conference in case anyone wants to tune in for that. But Viper is a rover that would land somewhere near the poles. If Viper lands at the surface, it is going to spray the surface with water vapor from its engines. And so the colors here predict the density of water vapor that will be deposited on the surface after landing. And now let's say the lander follows a traverse, something like this. You'll see that it's going to travel from a region where you might expect a lot of water to be deposited to a region that's not so contaminated. And so by comparing and measuring predictions, by comparing predictions like these with real measurements, we can get an idea of what really happens and refine some of the parameters in models even better. We can also measure water in the lunar exosphere. This is something that's been done before, even during the Apollo era. So, for instance, this is the Apollo 12 superthermal ion detector experiment, SIDE. It's about the size of a shoebox if you compare it to the astronaut footprint next to it. And it measured exospheric ions. And it saw traces of gases that were released by the Apollo lunar module during descent. So the white bars here show the density of a whole range of different gases. On the y-axis is molecule flavor, atomic mass, or molecular mass in the appropriate units. So the densities in white are how much you saw 14 hours after the lunar module landed, and then 58 days later, you'll see that you're seeing less of those exhaust gases because some have been destroyed by sunlight, but they're still persisting. But looking at the rate of decay can tell you about the processes that shape the water cycle and also the ammonia cycle and all of these other volatile cycles that coexist. And so taking a step back and looking ahead, I think these are some of the messages that I wanted to leave you with. I really do sincerely think that understanding water on the moon is not only a lunar science question, but it is a solar system science question, and it has bearings on so many other interesting science questions. And there's still so much to do in terms of measurements, in terms of creating models, running experiments. I think, one of the things I like about lunar volatiles is that it's a topic of research where there's room for lots of different people, lots of different ways of doing science, and I think that's what makes it a really interesting field to work in. And I think there's also a bigger question here that emerges from some of the work that I touched on later. So I think when we think of planetary science, it's sometimes about maybe three big questions. It's about where are we in the solar system? How did we get here? And where do we go next? And I think there's a fourth big question that we're only just beginning to understand, which is how do we change, whether that's temporarily or permanently, the environments of other worlds that we visit? I think that's a question that's going to become more and more important as we explore the solar system and solar system worlds at closer range. And the moon might be where we really begin to understand that question scientifically and think through the implications. And so my last slide is just some acknowledgements, because of course the science doesn't happen without a lot of people. David Goldstein, Philip Verghese, Larry Trafton were my excellent advisors at the University of Texas at Austin. Dana Hurley, Ben Greenhagen, and Wes Patterson hired an aerospace engineer to be a planetary scientist at APL. I'm also part of two amazing survey teams. One team ended its contract and became another, and also the incredible Lunar Reconnaissance Orbiter team, which has returned a lot of data that's shaped our current understanding of the moon. And last but not least, the simulations that I do were powered by the Stampede supercomputer at the Texas Advanced Computing Center, which I had access to through an excellent NSF program called Exceed, which I highly recommend if anyone's looking for a supercomputer. And so with that, I will stop sharing, and hopefully we have a little bit of time for questions. And in case we don't, feel free to reach out to me. My email address isn't hard to find. It's my first name dot last name at jhuapl.edu or at gmail.com. Either one works. But yeah, with that, I will stop talking, and hopefully we have some time for questions, and I can see the chat window now as well.